prevailing view among scientists is that current cosmological models still provide the foundational explanation for the universe's origins. Central to this framework is the Big Bang theory, which describes how stars, planetary systems, and eventually life, including humans, emerged. Despite its unconventional name, the Big Bang outlines a compelling narrative of the universe's earliest moments. All matter and energy were once compacted into an unimaginably tiny point, far smaller than a head of a pin. From this ultra-dense origin, a tremendous burst of energy and matter, what we call the Big Bang, set the cosmos into motion, sparking an ongoing expansion that continues to this day. However, as our understanding of astrophysics and cosmology deepens, cracks in this long-standing theory have begun to appear. The launch of the James Webb Space Telescope, JWST, the most advanced and powerful space observatory ever built, was expected to reinforce the Big Bang model. Yet, within just its first year of operation, the JWST delivered findings that astonished the scientific community. Its unprecedented ability to peer into the farthest reaches of space uncovered galaxies so ancient that they challenged established assumptions about the universe's origin. These revelations have sparked intense debate, particularly around the idea that matter might have existed before what we define as the Big Bang. A breakthrough moment came when cosmologist Rohinatu, analyzing JWST data, identified a galaxy that appears to have formed shortly after the Big Bang. Now considered the most distant and oldest galaxy ever discovered, this finding sent shockwaves through the scientific world, highlighting the JWST's transformative potential. The telescope is shedding light on a critical period known as the Cosmic Dawn, roughly 200 to 300 million years after the Big Bang, when the first stars and galaxies began to shine. The JWST's discoveries are already clashing with traditional models, revealing galaxies that exhibit properties once deemed impossible at such an early stage of the universe. The surprising abundance and complexity of these early galaxies have ignited a scientific reevaluation, prompting researchers to urgently revisit existing theories. As scientists dive deeper into the JWST's data, they are confronting profound questions about the fabric of the universe and the fundamental forces that shaped its infancy. The telescope's design gives it distinct observational advantages. It operates about 1.5 million kilometers from Earth, free from terrestrial interference, and is cooled to near absolute zero by a sunshield the size of a tennis court. Its massive gold-coated primary mirror and ultra-sensitive instruments allow it to observe parts of the universe that were previously hidden from view. This golden age of discovery is just beginning. By examining the galaxies from this formative epoch, cosmologists can rigorously test, refine, or even overturn long-held theories. Many questions remain unresolved, particularly concerning the roles of dark matter, dark energy, and the complex interactions between gas, dust, and star formation. But thanks to the JWST, we now have the tools to explore them like never before, opening a new chapter in our quest to understand how everything began. At the outset of its mission, expectations for the James Webb Space Telescope JWST were modest. Scientists anticipated it would detect only a limited number of faint, early universe galaxies. However, these early predictions were rapidly outpaced. The telescope's initial images of the ancient cosmos revealed a staggering abundance of galaxies, diverse in age, size, and brightness, far surpassing what experts have foreseen. This overwhelming stream of galactic data has ignited a scientific frenzy to redefine what qualifies as the earliest massive structures in the universe. As discoveries continue to emerge, even the most seasoned astronomers find themselves astonished. The growing body of JWST observations has not only mesmerized the scientific community, but also captured the imagination of the public, as these distant galaxies prove to be far more complex and evolved than previously assumed. Some researchers suggest that anomalies in the data could stem from misinterpretations of JWST's large-scale observational methods. Yet, the prevailing view is that these findings mark a profound shift in our understanding of cosmic history. The telescope's revelations offer a compelling glimpse into a universe more intricate and perhaps more enigmatic than past models had envisioned. The existence and characteristics of these ancient galaxies are now challenging the very foundations of cosmological thought. While some scientists are optimistic that current theories can adapt to these revelations, others argue that they may represent the first signs of a deeper, more layered reality, One fundamental question continues to echo. How did the structured universe we observe today arise from the chaotic crucible of its origins? JWST's early discoveries may not only reshape our perception of the Big Bang, but could also prompt new interpretations of distant galactic systems, insights that may eventually revise our understanding of the Milky Way itself. As Mark McFadden, a senior science leader at the European Space Agency, put, the purpose of building instruments like JWST isn't simply to affirm existing theories. It's a question and potentially dismantle them. You never know what might be overturned. The concept of JWST dates back to 1985, years before the Hubble Space Telescope launched, when Garway, then director of the Space Telescope Science Institute, SDSCI, was tasked with envisioning a successor to Hubble. Despite early skepticism, Weir and a dedicated team laid the groundwork for what will become the James Webb Space Telescope. Unlike Hubble, which focused on capturing visible light, JWST was deliberately designed to observe the universe in infrared. This choice was crucial because the expansion of the universe shifts light from the most distant galaxies into the infrared spectrum, rendering them invisible to optical telescopes. With its massive ultra-cold mirror, JWST can detect these faint signals, allowing scientists to peer deeper into cosmic history than ever before. The need for such a powerful observatory became undeniable in 1995 when Hubble's deep field image exposed thousands of galaxies in a tiny, seemingly empty patch of sky. That groundbreaking moment revealed the immense richness of the early universe and underscored the urgent need for a next-generation telescope with even greater range. After decades of planning, development, and an investment of approximately $1 billion, JWST launched on December 25, 2021. By July 2022, it was fully operational and ready to embark on its groundbreaking scientific mission. Programs like the Early Release Science, ERS, initiative and the General Observing Program were launched to search for the universe's first galaxies. Though initial projections were cautious, JWST's first data, released, quickly upended expectations. Its observations are already testing, and in some cases overturning long-held models of the universe's infancy. The findings serve as a powerful reminder of why pushing the boundaries of exploration and investing in cutting-edge technology are absolutely vital. With each new data transmission from the James Webb Space Telescope, JWST, scientists edge closer to potentially rewriting our entire understanding of the cosmos. When the first signals from JWST were released, the excitement was palpable. Researchers who had spent years developing analytical tools and theoretical models were finally able to apply them. Rather than waiting for the traditionally slow peer review process, many chose to publish their initial findings instantly through preprint platforms like AR14. This approach enabled immediate access and swift feedback, sparking widespread discussion, particularly on platforms like Twitter, where experts could share critiques and insights almost in real time. Cosmologist Rohin Naidu referred to this phenomenon as science by press release, highlighting the rapid visibility and feedback cycle that unfolded. While this openness accelerated collaboration and idea exchange, it also raised concerns among some scientists about the potential erosion of the rigorous scrutiny typically associated with peer-reviewed science. Klaus Pontoppidan, lead project scientist for JWST at SDSCI, cautioned that although fast-track discoveries foster innovation, they risk overwhelming the deliberate pace and careful checks of the traditional scientific method. Still, despite the logistical and epistemological challenges, most researchers agree that the trade-offs are worthwhile. The unprecedented volume and significance of discoveries flowing from this high-stakes mission demand new approaches and offer rewards that far outweigh the hurdles. For now, the Big Bang Theory remains a dominant framework explaining the origin of the universe, including the birth of stars, planets, and ultimately life. Despite its somewhat misleading name, the theory describes a coherent, science-based narrative. All matter and energy were once compressed into an unimaginably small, dense singularity, smaller than a grain of sand. From this point, a monumental burst of energy initiated the expansion of the universe as we know it. However, as JWST continues to peer deeper into cosmic history, its revelations are beginning to expose cracks in this long-held model. The discovery of galaxies forming far earlier than current models suggests the timeline of the universe may be more complex than previously thought. These anomalies don't just challenge the Big Bang's chronology. They open a door to entirely new frameworks for understanding everything from subatomic particles to colossal galactic structures.